This is our car park system connection. First and foremost, power connection, the STM32L42KC is powered by connecting the VDD pin to 3.3 volt source and the VSS pin to common ground. For 7-segment relay connection, which is using all the port A, PA0 connects to segment A through 220 ohm resistor, PA1 connects to segment B through a 220 resistor, PA7 connects to segment C through a 220 resistor, PA2 connects to segment D through a 220 resistor, PA3 connects to segment E through a 220 resistor, PA4 connects to segment F through a 220 resistor, PA5 connects to segment G through a 220 resistor, and last PA6 connects to decimal point D through a 220 ohm resistor. Lastly, output LED connection, which is the grand LED, is configured as active flow, with the cathode connected to PB5 and the anode connected to 3.3 volt via 220 resistor. For input button connection, when the car in, the button is wired to PB0 with 10k ohm pull down resistor to ground and the opposite side to 3.3 volt, whilst the car out button is wired to PB1 with 10k ohm pull down resistor to ground and the opposite side to 3.3 volt.
So now we are going to discuss about the flowchart that shows the main operation of the parking monitoring system using the STM32 microcontroller. So basically, the program starts by initializing all GPIO pins for the button, 7-segment display and the LED. After initialization, the system enters an infinite loop, which allows the program to run continuously. So inside the loop, the system will first read the in and out button inputs. To ensure that each button press is counted only once, we are using a rising edge detection method. When the in button is pressed, the car count is increased, and when the out button is pressed, the car count decreased. This will ensure that the system remains within its valid limits. Next, the program checks whether the car count is less than the maximum parking capacity. When there are parking spaces available, the system will operate in available mode by displaying the number of vacant spaces on the 7-segment display and turning the green LED on. If the parking capacity is reached, the system will switch to full mode. In this mode, the LED is turned off and the display alternates between the letters F, U, L and L to indicate that the parking lot is full. Then the loop will repeat continuously to ensure real-time monitoring of the parking status.
Now, let's look at the functional block diagram. The system is divided into 3 main stages: input, control and output. It starts at the input block, which consists of 2 active high push buttons. When a car enters, the in button sends a signal to the control block, which is our STM32L432KC microcontroller. The MCU first runs a debounce delay to ensure the signal is clean and doesn't double count a single car. Then, the MCU checks the current car count. If the count is less than our 10 space maximum, it increments the count and updates the output block simultaneously. The 7-segment display is connected to port A and shows the numerical vacancy. Meanwhile, the status LED is connected to pin PB1. It uses active low logic, meaning it stays on to show availability and only turns off when the system hits the full stick. When the MCU detects that the car count is no longer less than maximum space, it triggers the display to cycle through the letters FULL with a 500 millisecond delay per character and switch the status LED to off.
So our first component is we use the configuring Nucleo L432KC. Next, we use the 7-segment display, which is common anode as output. Then we will use a push button, which is our sensor. First button is for the input, which is car enter the car park. And then we use a push button for the car out. And for the push button, we set it as a active high. Next, we use 2 types of resistor. The left side is a 10 kilo ohm and the right side is a 220 ohm. Lastly, we use a LED green, which is if we turn on when the number of vehicles in the car park is less than 10, which is as our output. And we set it as a active low.
Alright, this is our circuit for the car park system. As you can see, I press the button for the input and it will display full and the number is decreasing and the LED is not on. Then I press the second button, which is indicate the car out, and you can see that the LED will display on and the number of the segment will increase, which is indicate that our available in the parking.
The code begins by defining specific pin number for 2 buttons and LED to make the rest of the code easier to read. A constant array name segment map store the hexadecimal value required to display the digits 0 through 9 on a common anode 7-segment display. Specific hash codes are also defined for individual letters such as F, U, and L to allow the system to display text. The image shows a custom delay MS function that uses the ARM Cortex-C timer to create precise timing without relying on external library. The code calculates the number of clock cycles needed for 1 millisecond and load that value into the timer loss register. It then enters a loop where it continuously monitors the count flag within the control register to see when each millisecond has elapsed. Once the requested time has passed, the timer is disabled to save power before the function exits. The GPIO init function start by enable the internal clock for port A and port B so the pin can receive power. It configure pin PA0 through PA7 as output by modify the MOHD register, which will allow the microcontroller to control the 7-segment display. The code use bitwise operation to clear existing setting before forcing the pins into output mode. The final section of the image shows the beginning of configuration for the entry and exit button on port. When the car count reach its limit, the code turn off the green LED by writing a high signal to the ODR register. The program then executes a sequence that displays the letter FUL and L1 after another on the 7-segment display. Each letter is shown for exactly 500 milliseconds, creating a flashing or scrolling full message for the user. A warning comment at the bottom notes that because the animation uses blocking delays, the system will not be able to detect new button press until the animation finish.